Hello and welcome to this coding stream. Today I'm going to be playing around in Rust for a little while. This is the first stream, so I'm not going to make it too long. So today's project is emulating one of these. This is an Acorn A3000 from around 1989, 1990. It's one of the first ARM-based computers, and it ran this RISC-OS operating system. So the ultimate goal here is to have an emulator of one of these running in the browser. So right now I am writing it as a native version in Rust, and hopefully eventually I can figure out how to get it compiling to WebAssembly. Actually, the compiling is easy enough. Getting it to actually run in a browser, yeah, not so much. I might need to get some advice on that eventually. So where it is at the moment, this is the approach I took. I created a CPU object. What do you call them in Rust? It's an object, a struct. It's not exactly a class. So it has the ROM loaded in as part of the memory, and it also has an area of RAM and a register file. So that's about it at the moment. What it does is start at the beginning and just execute each instruction until it gets to one that I haven't implemented yet, and then it panics on purpose. So far we have a branch instruction implemented, because that's the first thing that happens when it hits the reset vector. Let's see, I got some documentation for that somewhere. Let me see. This is actually a copy of a book that VLSI put out in the 90s. They send a free copy to anyone who asks. My original one went missing. I think I lent it to someone. I eventually managed to find a couple of copies online. Where are vectors? Okay, so can I annotate this? There we go. So reset vector is the very first one. So the first word in the operating system ROM is a branch from here into ROM, where it starts executing. And what I discovered is that it starts executing in a weird way. So it starts here at 0, branches into the ROM, and executes what looks like a memory test pattern. So we've got this F2, F1, F08, F04, all the way down here, which looks like nonsense that shouldn't work. However, each one of these words has a top nibble of F15, which in the ARM instruction set is a conditional that means never execute this instruction. So I guess it's kind of a clever little test, because it can go through all these without actually executing them. So after we go through a few of those, we get to here, which is the first real instruction, and that loads whatever is pointed to by the program counter into register 0. In ARM, the program counter is always 2 words ahead of what you're executing because of the pipeline. So this is loading a 0 into R0, and then there's an ALU instruction. And I have not implemented those yet. So that is going to be the first job for today. Start doing some of that. There's my webcam. There we go. All right, so instructions. So we got a table here. It's just like a jump table. It matches on, where do we dispatch? Matches on the nibble after the conditional. So we have 4 bits of conditional, and then we take 4 bits to decide what to execute. The opcode is not exactly 4 bits wide, so that's why there's 4 of some of them, 2 of some of the others. But it more or less works out. So for example, for the branch, there's 2 of those because there's 3 bits that says it's a branch, and then 1 bit. You can see it on here actually. There's 3 bits. 101 says that it's a branch, and then the 4th bit says whether it's a regular branch or a branch with link, which means that it copies the program counter into the link register, so you can jump back afterwards. Okay. Where are we? So we execute, we got the execute for branches. So each type of instruction, as well as the execute, there is a format function, which is what gives us these things. So for some of them, that's fairly simple. For a branch, there's almost nothing to it. For a load or a store, that has to take into account all the different ways of loading the register, so either directly or with a shift left or right, or a rotate right, whether or not it's what does it deal with, indirection or not, and potentially right back, which is like the equivalent of putting a ++ on a pointer read in C. So we have the ALU ones are pointing to unimplemented at the moment, which is where we get this panic from. So I have a document open here that tells me which ones they are. Oh, hello. Ah, I already have them in there. So where the heck are they? Ah, here we go. So execute ALU. So an ALU instruction looks like, why is this not changing the screen? God damn it. There we go. Let's find it. ALU instructions are 001 followed by an opcode. So that's why we have 4 of them. What? Oh, that's not a 1, that's an I. 00I opcode. So yes, that's why there's 4 of them. Because there's 00 register, 0, 00 immediate, 0, and then 1 for each of those as well. So the first thing we need to do is take a look at this bit here, which is bits 21 to 24. So we take this here, shift it down to here. That's not what I wanted. And then mask it off. That's rubbish. Alright, so execute ALU. So let's say let opcode. I should also point out that this is my first time writing anything in Rust. So anyone who knows Rust is probably going to look at this and be screaming at the screen. So we do shift down 21 bits. Oh, what am I doing? Let opcode equal instruction shifted down 21 bits and masked with that. Right? Why is it giving me a... Where's that error? Oh, it's gone. Weird. So once we got the opcode, what should we do? Switch it to different functions, maybe? Yeah, we could do that. Do we want a jump table? Do we want a match? Do we want an if? Let's do it as a jump table, why not? So how do we do one of those? Const instruction handlers. Instruction handlers 16. Should we make them instruction handlers? Yeah. So you're going to have the same signature. Can I put a const in a function? You have to specify the type for an instruction handler, for a, what you call it. That's actually the type. And then fill it in with exec unimplemented. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Alright. So what's the first one going to be? First one is and. So I need these registers, but I don't want to decode them every time, so I should probably be passing those in. Okay. So maybe I should decode those here. Maybe I want a different type for those. How do I define that type? Down here. Okay, so basically type whatever equals, and then the signature, more or less. Alright. So do any of these use anything that's specific to one of them? They don't, do they? So I can define let's see. Let's define a type called ALU instruction handler, and put that in there. And we'll say it takes the registers and the memory. Instead of taking this instruction, we'll take a destination register. Destination register, so it's always a register. A register number for the first operand, that's always a register. And then operand 2, what are our options? Immediate, register, so for the register it has the register number and the shift. And the shift logic, we have already in the load and store, so we might want to bring that out. Okay, so let's call this RD and say that is a unsigned 32. Oh, hang on, that's not the value, is it? So what have I been using for those? Okay, I've been using U32s for register numbers, even though they're only 4 bits wide. So destination register and then operand 2 will figure out what the value is and pass that in. So that's going to be up to okay. So we can't use unimplemented there, so we need a exec ALU unimplemented, which takes all this business. Am I still on the wrong screen? So that takes all this business. Where is it? Here. Keep an eye on the time. And what does it do with that? I guess call the other one exec unimplemented registers memory and instruction. We don't have the instruction. I guess I can pass in 0 because they're all going to disappear eventually anyway. They're just placeholders. So these are all ALU unimplemented. There we go. That makes that happy. So we've got that. We need to, first of all, decide whether, where is that bit 25? Oh, it's all the way up there. Okay, so bit 25 is immediate. So let immediate equal instruction 25 not equal to 0. Is that the right way around? Yeah, 1 is an immediate. So if it is an immediate, then yeah, we need to assign this to something. So let's say let up to equal if immediate. Oh, you don't need those in Rust. So it's just the number and the amount to rotate to the right in 2 bit shift units. Interesting. All right, so should we call that? Let's say value. It's kind of a rubbish name, but equal instruction ended with that, and let rotate, rotate, why can't I type? Rotate equal instruction shifted down by 8 and masked so that 8, 9, 10, 11, so it's that. Except it's not that. Because it's 2-bit units, so we double that. Times 2. And what is it? Right rotate. How do we do that in Rust? So return value something rotate. Let's look that up. Rust rotate right. Nope, that's for slices. So this is shift right, which we've used elsewhere. So let's see if there's a rotate right in the same documentation. No. We're going to have to do it manually. Actually, how did I do it before? Where did I do this? In load. So I did it like this before. So we call this rotate, and this will be immediate. Okay, so we take the immediate, which is 8 bits, and we rotate it as though it were a 32-bit word. Right, because that means we can take an 8-bit and rotate it round so it's at the top if we need to. Alright, that is covered. So if it's 0, then it's a register. So let's get the register number, which is just instruction shifted down. Oh, no, not even that. Instruction and looks F. And then we've got the shift field. Now hopefully this shift thing here is the same as for the load. So we've got left, right, arithmetic right, and rotate right. That looks the same. So where did I have it? So shift type, take the shift amount. All right. So let's get a shift type. Where's the shift type? Okay, this is confusing. So this is out of this field. So, whoa, what is this? Bit 4 is always 1. Ah, okay, so that's, what is that telling us? Oh. So the amount to shift by can come from a register as well. So shift amount. So we can have 5 bits of shift amount, or we can have 4 bits of register and a 0. So we're going to have to test bit 4 to get shift amount. So let's get shift type out first. So that's bits 5 and 6. So instruction shift down 5 and ANDed with that to get 2 bits. If it's clear to do that. So then we need to do let shift amount equal if alright, to test a single bit we only need to AND it, we don't need to do the shift as well. So if instruction AND with 1, so it's in bit 4. So if that's not equal to 0, then that is register, otherwise it's immediate. So in the register case, we got rs equals instruction shifted down five, 6, 7, so 8. Shifted down 8. And then ANDed with 4 bits. 8, 9, 10, 11. Okay. So then what we actually return is we're going to get that. So we do registers dot that could potentially come from the PC, although there's no reason for it to. But if it did, oh man, if we use the PC as a shift register, should that include the flags? Huh. Does it say in the documentation? Doesn't say anything about that, as far as I can see. All right. Fine. I'll just do it as is. So that's what we return. So in the case of an immediate, And I did say the bottom byte. Should I? It says the bottom byte, but it's really only the bottom nibble. Wait. Shift amount is specified in the bottom byte. Does that make sense? I'm going to put it anyway, because that's how it says it is. So, immediate case, the actual shift amount is a 5-bit unsigned integer. So it is simply instruction shifted down 4, 5, 6, 7 bits, 7, 8, 9, 10, 11, and ended with 5 ones. These should not have semicolons on the end. I think it's weird that in Rust it will return the last expression, but only if there's a semicolon, not on the end. So what is this complaining about? Nothing. The Rust plugin for IntelliJ seems a little shaky. Sometimes you can comment something out and then uncomment it, and suddenly it works. So when there is one of these, you don't necessarily. Ah, there we go. There's a syntax error. Ah, semicolon on the end of the assignment. Right. Gotcha. That means this is going to need one too. So we've got our shift amount and we've got our shift type, so we can do all this. So we can say let, oh, hang on, we've already got that. Let op2 equal this. So we should maybe take op1. Yep, take op1. Here, let op1 equal. Do we get Rn somewhere? No, let's get that first then. Rn equals instruction 16 ended with OXF. So then we can say op1 equals registers dot get what dot reg rn. So now we've got everything we need to call into there. So we can just do ALU instruction handlers, opcode, we execute it with the registers, the memory, RD somewhere. No, we didn't pull that out yet, did we? RD, we don't need RN. That's going to be op1. Let's change that in here as well. Op1, op2. So let's pull RD out. Let RD equal instruction shift down 12 and mask it off. Nice. Let's see. Quick send a message. Well. Oh, my tax refund has arrived. That's handy. Oh, so many errors. Let's implement one instruction then. We're going to start with let's look at some of these errors. So unshifted in our case is did I even get it out yet? Huh. Wait, what? Hold on. I've got RM. What am I doing here? I've got RM. You've got the shift field. So I need the unshifted value. So we've got well, the unshifted value is what you get from RM, so equals registers dot reg RM. Yeah, okay. So now we do our unshifted. Let's see, that's unused, that's fine for now. Oh, 81. That should be value. Okay. I guess I just cast this. I don't see that there's anything else I can really do with that. Okay, whoops. So we can see here there's a completely different error that isn't mine. Attempt to shift left with overflow. It's an 81. Attempt to shift left with overflow. What does that mean? What does that mean? So yes, I have attempted to shift left here. Okay, first of all, I'm going to check there isn't a way to do this without having to do it manually. So rust, rotate right bitwise. See if this has it. Rust, where are you? Nope, let's just go shifts. I don't think, there is a function to do it. Alright, rotate right with N. So this should just be value dot row. Ooh, not there. And why isn't it there? Is this something I have to include? Yeah, but this says that it's actually on the U32. Try compiling it. We got that this time. Thread main panicked it, not yet implemented. Cool. So let's find out which opcode is actually being executed there. So as soon as we get that opcode, let's see, let's just take a format. LU opcode blah. LU opcode 4. So maybe what I should have done is implement that one first. And it is it's an add. All right. So we go to here, copy this. Exec LU add, all that stuff. So this should be easy enough, right? We just we need to set that. Could we just return the value and have the function that's calling it set it in the register? No, we can't, because test and compare don't actually set RD. Okay, so this is a regular add, no carry. So let's do registers dot set reg. RD to op1 plus op2. Okay, so now we've got to go back and check what happens if RD is the program counter. It says a lot about what happens if RD is not 15. R15 is an operand. Here we go. If R15 is used as an operand in a data processing instruction to present different values depending on which operand position it occupies, it will always contain the value of the program counter. It may or may not contain the values of the PSR flags as they were at completion of the previous instruction. Okay. In RM position, it includes the flags. Alright. Let's go back here. So RM unshifted reg, no flags. Well, hang on, what did that say? Flags or no flags? With the flags. In RN or RS positions, no flags. So RS. So that is no flags. Where else did I use it? RN. Where is RN? So we get up 1. So this is no flags. Good. But what happens if it's the destination? We're onto a different instruction here. Multiply is separate, I think. Yeah, multiply is not included in there. So we don't know what happens if it's the destination. I mean, does it depend on whether the S bit is set or not? Okay, all right. I'm going to think about that. We might have to pass the S instruction in. The S bit in, so I know whether to set those. Because these test ones are different. They don't set RD, so I can't just test RD. So I'll have to do it in there. So I'll do a function which I can call, which sets the appropriate status flags at the end of a function. Alright. Good. I'm going to stop there. I might do another one later on where I implement some of these fully. Alright, that's it. Bye for now.